So my name is Nathan Kaufman. I'm the product manager for Fibersim here at Siemens. I've actually been here for 14 years, back from the early Visagy days. So I'll go through what's new in Fibersim 17. So we're going to cover, from an agenda, we're going to look at basically some of the main enhancements in Fibersim 17, including forming, planar cross-sections, Teamcenter publish, explicit layer splicing, and some of the smaller enhancements we made as well. So with Fibersim 17, we're actually entering a bit of a new area with our forming for designers capability, which has the goal of being kind of a design tool for formed parts, which is accessible to designers that actually are using CAD as opposed to finite element models. The goal is to allow you to assess producibility of multiple concepts in a really short period of time, to quickly reduce the number of viable concepts to then pass on to further in-depth analysis when you're looking at forming as a potential manufacturing method. And to really bring in this physics capability, which, again, is a new area for Fibersim. So when looking at where the forming for designers capability sits in the design life cycle, it really depends on kind of design stage. So there's this natural trade-off that happens between the speed of the simulation and the accuracy of the results. So based on that, you have kind of these multiple areas in terms of concept selection, design validation, et cetera. And looking at the concept selection phase, where you have a bunch of different ideas, you want to sort of evaluate them quickly. We've actually proven that the Fibersim producibility simulation, which is entirely geometric, is actually a very useful tool for understanding when you might run into producibility problems with a particular geometry. But it kind of ends there. And that's where the forming simulation really picks up with this new physics-based capability. Still from CAD, you're able to both address or set up a forming simulation that accurately represents maybe what the process that you're looking at applying to a given part type is, and then actually highlight some areas where you might want to narrow down on a particular design that will meet your needs as you get into the performance area. And then from there, you can kind of trade off or hand off onto the CAE world to allow, really full in-depth finite element analysis to ensure that you have a producible part. So forming for designers is just that. It's a design tool for formed parts. Again, it allows you to quickly assess the producibility directly from within CAD and reduce the number of concepts for further analysis to sort of reduce the churn. The big thing that makes this enhancement really unique is it's a totally CAD integrated tool that really requires no special knowledge as far as CAE kind of understanding in terms of meshing, boundary constraints, et cetera, that would typically be required for some of our competitive solutions that are trying to run these physics-based simulations. So you can do it directly from kind of the designer's toolbox inside of CAD. So with that, we'll go through a quick demonstration. This is actually a video, so hopefully it plays all right. I think Andrea will let me know if it doesn't, how it works. So the forming simulation, we have our own sort of customized menu here, and kind of the first step is to really set up what your actual forming process looks like. So we have these press tools that you would model just like you would a laminate surface. You also have this surface normal, the motion direction. So you have these, you can have kind of as many tools as you want. In a typical match metal process, it's kind of a minimum of two, an upper tool and a lower tool. And we can show you what that motion looks like. Once you have that tool configuration set up, the next step is to go into the actual forming simulation itself. So this is a little bit separate from the rest of Fibersim in that you're not actually running on 3D plies. The first step is to link your press tools, and then whereas our standard Fibersim process is to use 3D curves on a surface to determine what the boundaries are. In this case, and then simulate to get a flat pattern. In this case, we're actually starting from a 2D blank and then simulating the process of forming that blank onto the tools. So here we do have one control for the mesh size, which determines is the primary determining factor for the speed accuracy question. So in this case, we're going to look at a mesh cell size of 15 millimeters, and you can see a little preview there to see what that 2D mesh actually looks like to ensure that you're not, doing something that's going to take 4 days to run. We have some basic material requirements that are set up. These are pre-populated in the list, but are accessible to the designer rather than buried in a database. And then we have the ability to just run the simulation. So what this does, again, is unique to Fibersim. It's actually kicking off an external process that will take those inputs and run the simulation. So it has a % complete based on a number of frames, and also estimates the actual time required to run the rest of the simulation. As it's running, this is actually running, again, a separate process in the background. We have the ability to effectively update the display to see where you are in the process. And you can see every time we click that show latest frame button, the tool moves a little lower down and starts to push into the mesh. Again, unique to the simulation is that it's actually running in the background. So you can go ahead and save the form, maybe set up another simulation to run in parallel. This is really a unique look at sort of standard process in Fibersim, as it allows you what we feel is sort of a viable workflow is maybe set up a couple of different simulations, sort of ideas of how you would want to actually set up your part, and then run them in parallel. So in this case, we're going to take a look at a smaller simulation, just looking at a patch of the part rather than a blank that covers the entire surface. And we'll kick that simulation off as well. And you can actually see what the status of those two simulations are. We can report just in table mode with using standard Fibersim capability. You can just see kind of where those simulations are in their process. And you'll see that time estimation fluctuate, go up and down, especially early on. As you get closer to the end, it's able to detect or become really more of a countdown. And now we get to the point where both simulations are complete, and we'll start to actually look at the results. So we have a separate area to look at to view the results, where when you run a simulation, it will kick off a viewer object as well. And now this actually loads the data from a FSF file, which is stored externally. So what we can do is basically load that in, and when we run this playback, you can start to see the tool converge on each other. And this is actually loading the data into session. Once it's been complete, you can actually step through one frame at a time. And you can see this particular simulation has 200 frames. And we're running at an increment to sort of give you a decent animation. We can also turn off the tool so we can just look at the mesh. And again, this is based on a 15 millimeter cell size, so it's a little bit coarse. But just like with Fibersim, we have the ability to turn on fiber paths as well. You can customize your warning and limit angle here to see where you might have some problems, to help see if shear is the thing that you're worried about. Although we found in some cases it's not so much the shear angles as it is sort of the 3D wrinkles that are really the problem. But in this case, you'll see some high shear areas starting around those bosses. We can also turn on multiple different display types depending on what you're trying to evaluate. The other capability, because we have these external FSF files, is you can actually view this in an empty model. So you can share this FSF file and anyone can actually view it using the CAD system to take a look. So in this case, this is a much finer mesh. This is a 5 millimeter cell size, and you can see much more detailed results that have been run. So again, the idea is you start at kind of a coarse level, and then you can start to fine tune and iterate as you start to converge on a solution. In this case, now you can really start to see some definition around those wrinkles and some of the sort of 3D waviness that shows up.
Nathan, we do have a question whenever it's a good time for you.
Yeah.
Okay.
Sure, go ahead.
Aniruddha wanted to know, if there is no meshing, how are the results coming in? How are they accurate?
So what we do, there is meshing. It's just not, there's no user input to the mesh. The only user input is on that mesh cell size for the blank, which is sort of the determining factor for the sort of contact accuracy for that blank. In the background, when we kick off a simulation, Fibersim actually pulls the visualization mesh off of the CAD system. So those 3D surfaces that you see in the CAD system, which are actual CAD surfaces, they create a mesh in the background just to be able to shade it. And that's actually what we use for the tools when we run the simulation. So it eliminates any mesh issues, as far as like if you know, anyone familiar with meshing knows that it's not necessarily a push button operation. There can be a lot of problems that you may need to tweak and sort of fine tune some things. But by using the visualization mesh, which is generally not the best practice for CAE, it allows us to ensure that we always have a valid mesh.
Perfect, thank you.
Yep. So the next step in this little demonstration is to actually take a look at a design change to try to address some of those producibility issues. So we're going to increase some draft angles and the radii. I think it actually did update real quick. I don't know if anybody noticed it. But basically we're going to go, and we know those bosses are a problem. We're trying to make this part more composite friendly. And now we'll take a look at just the problem area and see if those changes had an impact. So here we have the results, and you can see that we no longer have any deformation problems around those bosses. So this is a pretty simplistic example of what that might look like in you know, obviously in some more complicated cases, it can be even more important to get really accurate results. So in this case, again, this is what our final shape would look like as far as the sort of formed part. And at this point, you know, I think we're happy that this part is in fact formable using a composite part or match metal forming. And I think we're going to step through some frames. So I'm going to go ahead and move on to the next one. So the next big enhancement in Fibersim 17 is actually sort of the finalization of a project that started with Fibersim 16, which is planar cross sections. So the first big area of enhancement here is the addition of the shaded and centerline profiles. So in addition to the line type, which is basically going across the top of the ply, we've added two new profiles to the toolbox to allow you to visualize what your layup is. Now, anyone that's familiar with composites knows sort of the criticality of having a valid cross section to be able to really understand what you're dealing with, because just looking at a 2D shape doesn't necessarily tell the full story. And the sort of traditional line style of the top of the ply, particularly when you're dealing with a lot of plies, it actually can be very difficult to distinguish between different components. So both of these profiles are sort of targeted at situations where you want to have a more unambiguous display. You know, the shaded components really provides the image that you see here, which is really a, you know, totally clear picture of what's actually happening. The centerline profile we added as a way to provide a little bit more of an intuitive option for viewing the ply definition. You know, it's going through the midplane of the ply as opposed to drawing the top of the ply. So it's more sort of standard from a kind of sectioning standpoint. You know, the big benefit here, you know, shaded, the planar cross section algorithm is extremely robust, and it, you know, with the addition of the shaded profile, turns what you know has been kind of a competitive gap for us in Fibersim into more of a strength. You know, now we have a very robust way to create a totally unambiguous display. And then the remaining planar cross-section enhancements are focused on building out the other options that we had had in place on the legacy 3D cross sections. So we've added a schematic style, we've added constant scaling, as well as translation along a vector. And while you won't necessarily need all of these options all the time, we've found that there are circumstances where you really need a full toolbox to be able to properly meet every need you have in terms of communicating a design. So at this point, with these enhancements, planar cross sections now have the full breadth to replace the legacy 3D cross section and really set the industry standard now for composite cross sections. So with that, we'll go through a quick demonstration of the new enhancements to Fibersim 17 around planar cross sections. Oop. So this is going to look at those options that we just reviewed. So the first step is to go ahead and create a planar cross section. So that's the ply layup that you would see. It's obviously not super clear as far as what is actually happening. So we can pick a plane. In this case, it can be picked directly from the part navigator. We'll go ahead and run this section with the default options and take a look. So the first thing you'll see here is, scale of 1 frequently is not very good for composite parts because they're very, very thin by design. So scaling is obviously a big factor that is kind of required. So what we're going to do is go ahead, previously we could scale it based on the material thickness. Now we've added constant scaling where you can just assign a single value to every single ply. In this case, we'll offset each ply by 1/4 inch. Again, this is just another way to draw a cross section depending on what your requirements are. What you will see is that we do not scale the core. So core is always drawn at its actual thickness because core is usually significantly thicker than the plies. The next thing we'll look at is the centerline profile type. So here, again, this is drawn across kind of the mid-plane of the ply. So you'll see, especially around that core area, it is actually the ply above it and the ply below it are equal distance from it. That's because those lines that are being drawn are at the mid-plane of the ply as opposed to the top of the ply. So switching back to line, you'll see this is the traditional way to look at it, where we draw the top of the ply, and you can see that it actually interferes with that bottom of the core. And then we'll just show again what the difference is with the midplane. So that's just another tool for visualizing. And then what I think is kind of the best thing here is this shaded profile. So, this really is completely clear results as far as what the actual cross section looks like. You can see we're doing a couple of things here where we're trying to highlight the edges using black as well as the labels. We've moved the label for the core into the middle of the object, but really there's no question as to what you're looking at here. You're not trying to decipher it, right? You can see all of the plies color coded according to their material, just as always. And along here, one of the things that comes with the planar cross section are these sort of bulbous effects around a ramp, which, especially as you start to scale it up, this is at a 1/4 inch scale, so it's almost probably 20 times what the original ply thickness was. So looking at this we can actually level out those ramps using a ramp ratio to basically control how quickly a ply consumes the drop. We've actually had some customers report that certain material systems, they have like an empirical value for how quickly a material will actually consume a drop as it drapes over another ply. And again, just another tool in the toolbox to help you, communicate your design. So the schematic section is something that, if you're familiar with, sort of old legacy cross sections, is certainly something that 3D cross sections had. We've added it now to planar cross sections. It's the exact same idea. The one difference here is that with core, we are draping the overcore plies over the core. So in other words, everything is schematic except for the core, which is drawn at its true shape. And then the plies that go over the core will drape over the core and then go schematic from there, which you can see from the picture. In the legacy, we had the core was sort of drawn as a box, which didn't really make any sense. So we've sort of cleaned that up to be as hopefully as intuitive as possible. And then the last thing that we added was this translation. This is another carryover from the legacy cross sections, although there it was called offset, which was really a misnomer. It was actually shifting the results. What this allows you to do is basically take the results of the cross-section, give it a translation distance, and shift those results in 3D space to somewhere else in the part. With planar cross-sections, we actually draw that big red arrow to indicate both the direction and the magnitude of the shift. And when we generate the results, it'll basically be at the end of that red arrow. That, by default, is just normal to the surface at the starting point of the intersection, but we can actually override that with an override vector as well. So you can basically put these sections anywhere in the part. And the last thing that we're going to highlight is the actual shaded surfaces. So because surfaces are new for cross-sections, we just wanted to show how they're represented in the CAD system. What we end up doing is basically creating a closed curve for every single apply. And then in NX, we create a bounded plane feature using that curve as a trimming curve. So you can see you have the bounded planes here. The curves themselves, just as in legacy cases, are just dumb spline geometry, but we've organized them such that the curves are in their own groups and the surfaces are separate, so you can actually control the visibility of each of those independently. And again, so that pretty much wraps it up for the planar cross-section enhancements. Again, it's kind of a full-fledged replacement now for the legacy product. And we think is really setting the standard for what a composite cross-section should be. Next up is the Teamcenter Publish capability. So with Fibersim 17 and Teamcenter 12.3 and later, you can now actually publish the Fibersim laminate, ply, and core definition into Teamcenter. There's a composite object model that was established in 12.3. That can now be populated directly from Fibersim. Previously, obviously, the composite definition was all sort of in Fibersim. We had different reporting structures that we could do, but this really kind of allows you to expose it to the enterprise and enables the digital thread throughout the Siemens suite to allow sort of different analyses and downstream consumption without having to actually open up the CAD system and look at Fibersim. So we'll go through a quick demonstration here. This is the last actual demo video we're going to go through. But what this is looking at here is, so the publish to Teamcenter, basically, you have a ply definition that's been defined in Fibersim, and we just want to effectively expose that in the Teamcenter environment. So what we've established is an expectation that you have a single top-level laminate. There's a limitation where each document can only have one laminate, part laminate published, and you can include the child laminates or not. It will include all of the child components, but you basically have to specify which laminate is the top level. So in some parts, you may have 6 or 7 different laminates, some of which aren't used. So there is a user requirement to actually specify which one is the part laminate, and you can see the components that it rolls up here. It does find that pad up laminate as a child, so we'll incorporate that as well. And we have an option to either include the nested structure, in which case we include the child laminates, or to do it flat. So this does require the extension to be deployed. There is, and it also requires these stock materials to be created in Teamcenter prior to the publish. And that little login screen you see is something that's required the first time only. So basically what that does is it saves the part and then publishes the data into a BVR within Teamcenter. So by sending the part to the structure manager, now we're looking at Teamcenter 12.3, you can see the laminate is actually what's called a GDE underneath that. So it's a non-revisable item, or a non-revisable object. So this is the standard BOM view. You can see all your plies here, but you can't see any of the composite data. So we're going to go through a quick demonstration of the configuration so you can see for a composite part how to show all of the data you want. We're going to remove the columns that we don't want, and we're going to add the columns that we do, which are these composite columns. So you have material orientation and step, which can be shown currently in the structure manager, and with 12.4, we're going to add additional columns as well. But that's going to require a Teamcenter enhancement. So now you see effectively a mirror of what you would see in Fibersim. You can see the entire stack up with the one caveat that all of it's impossible to see things in sort of the step-based structure. It's hierarchical. So the laminate comes first, and then all of the plies within it show up there. So next, we're going to dive into an individual ply. In this case, this is this GDE line. So it's actually the occurrence of the ply within the structure, not the ply itself. And if you're not familiar with Teamcenter, that may mean nothing to you. But it basically means that in order to find the actual ply information, we have to tunnel into the ply itself. This is not typically how we figure people will interact with this. It's more once it's in Teamcenter, it can be pulled. But here you can see all of the information that we're actually publishing. Basically, all the analysis information, a link to the material, and obviously the structure information as well. So the next step is to look at a slightly different approach. So again, this structure, you can see those step values aren't in order because they're this nested ability. So we've added this option, which is actually off by default, to include child laminates, because really those laminates are only for organizational purposes. They're not necessarily, useful from a manufacturing standpoint or even a design standpoint. It's really just to help work with Fibersim. So we can remove those from the structure, in which case it will output the child plies and basically reparent them to the top level. So here, when I refresh my structure manager view, you should be able to see all of my plies actually in the regular sequence step order. And now you can see the plies in the order that they would actually appear in the part. So the last piece of this Teamcenter published capability that has been released is actually around the data sets that we create. So prior to Fibersim 17, we had the ability to incorporate manufacturing data sets like flat patterns, laser files, and AFP files, and attach those to the item rev for the part. Well, with Fibersim 17, we've added this ability to flat patterns to actually attach the flat patterns to the individual ply objects, provided that you've actually created them. So in this case, we're going to create a flat pattern export. We're going to link all of our woven plies, because those are the ones that we need the flat patterns for. And we're going to set the export to Teamcenter plies. So this is the new option. And instead of attaching it to the top level item, it's going to attach a single flat pattern to each single ply in the list. It does require that you've run that publish operation first so that it can find the ply itself. But provided everything is set up properly, when you go and look at the details of that ply, you now see a data set attached, which is a flat pattern data set. And if we go ahead and look at the named references of that data set, you can see the actual DXF file that's associated with it. So now everywhere this ply travels inside of Teamcenter, it goes with the companion flat pattern, which really enables the full consumption of that everywhere you would need it. So for example, going downstream into manufacturing process planning, they now have the flat pattern that they need to go ahead and generate the cutting files and nesting files, et cetera. So the next big enhancement is actually kind of small one, we're calling it explicit layer splicing, which allows you to basically use CAD curves to directly splice layers. This isn't really radical, except that it eliminates the need of splice groups. So anyone that's familiar with splice groups, there are a certain number of assumptions and limitations that must be met in order to provide the automation that a splice group would provide, where it basically ships a bunch of curves and automatically creates all the offsets. Those curves have to cross the whole laminate. You can only do a certain number. And if you don't want to use splice groups, but you do want to use layers, previously there was no way to actually split up the plies or split up the layers into multiple plies without breaking the link to the layer, which means that your update cycle is kind of broken. So with this explicit layer splicing, all we've really done is added boundary closing to layer-based plies. And by enabling that, we now allow you to basically define any splicing strategy for any given layer without breaking the link. You can now maintain the associativity to the engineering definition, which enables one of the things we found a large majority of customers use is the manufacturing laminate workflow, where design will do a layer-based definition, and then publish out a manufacturing part that is, again, linked to that layer-based definition, and then use that for manufacturing. So it allows full support of that workflow without breaking the link in order to create your manufacturing setup. And then just a couple of other smaller enhancements that were incorporated with 17 as well. We had some wrapped ply improvements. One of them based on the layer-based wrapped plies is actually related to that explicit layer splicing, where you can actually take a multi-domain layer, so a layer that's like wrapped around a tube, for example, and convert that into a wrapped ply by basically adding the start and end curves at the ply level. And sticking with the theme of planar cross-sections, we've also added support for wrapped plies in planar cross-sections. So again, it now has full support of everything from within Fibersim. And the last piece is the CG Tech automated fiber placement interface for Vericut. Has been improved in a variety of ways, just made more robust to take better advantage of their new VCP product. We've incorporated some machine characteristics and ply constraints that were already captured within Fibersim, but weren't previously included in the old export, as well as better mapping of surfaces, laminate surfaces, so that if you have multiple laminates in a part, it does a much better job of actually maintaining that and allows you to get up and running a lot faster on the VCP side to produce your part. So in summary, just a couple of takeaways we wanted to reinforce here. With Fibersim 17, you can, quickly reduce the number of design concepts, for further in-depth forming analysis. We can create a completely unambiguous and pleasing result for planar cross-sections for all components and part shapes. There's no more limitations on planar cross-sections. And we can also use it in every case. If you need a schematic cross-section, you can create it. If you need to translate it, you can create it. Provides much more robust results than the legacy 3D cross-sections, and really more intuitive process. We're enabling the digital thread for composite details and exposing all that data to the enterprise with the Teamcenter interface, and delivering the full sort of support of the manufacturing laminate workflow, where you have a layer-based design that where the layer represents the engineering intent and the plies represent the manufacturing consumption of that. And another one that actually wasn't covered in this, because it's actually part of 16.1, was enhancements to the parametric zone transition splitter, where we enhanced that as well to be more responsive to design changes and keep the design intent in place, which allows full adoption of the multiply overlay zone-based workflow.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.